So this is what we're going to cover is the Astropy library, and just to give you a brief history of Astropy. We started this about 4 years ago. The goal was to standardize a lot of the libraries that were being developed for Python. I mean, the problem was that a lot of people were duplicating same kinds of functionality and leading to lots of sort of Python applications that weren't using the same interfaces, weren't using the same libraries or conventions, things like that. And I think we'd reached a critical mass of it was time to try and get everybody on board on the same, using the same kind of tool sets in developing applications. And we went as far as at the Space Telescope Science Institute moving in some basic things like PyFits and WCS libraries into AstroPy to sort of help foster that. It's turned out to be a very active project. There are a lot of contributors and people involved in developing these tools. A lot of work. I think it's not appreciated how much work goes into making sure everything is consistent in its user interface and how it works, and that it works on all the platforms we're supporting. It works for both Python 3 and 2. And the work that goes into, there's a substantial amount of work to make sure that it continues to work for all these things, and I'm not sure that's always appreciated. And the people that will be teaching the tutorial today, aside from me, are quite active in developing and supporting AstroPy. I thought I'd just highlight what we weren't making this. It's not introduction to Python, though if you don't know Python, I think you'd still get a lot out of it. I'm curious, how is there anybody here that hasn't really used Python much? Okay. It's not comprehensive for all of AstroPy. There are too many libraries and tools to cover in this short amount of time. We're just going to cover some of the basic aspects of AstroPy. We are going to focus on fundamental things that aren't really applications in their own right, but that you could use to build your own applications or to interface to applications. And one other thing we're not covering are other packages of tools in Python. That we're just focusing solely on AstroPy. We'll use Matplotlib and Numpy, of course, in doing this, but those are sort of assumed tools that we use in conjunction with this. So the outline of the tutorial, I'll just give you a brief breakdown of this. You're seeing the introduction right now. And we're breaking each of these sections into equal amounts of lecture and exercises. Part of the exercise time will be you working on the exercise. I think we're going to reserve a few minutes at the end of that exercise period for for us to review the solutions to the exercises. But the areas that we're covering are units and quantities, working with tables, data access in general, both for Ascii and fits data, dealing with coordinates and coordinate systems, time, and a little bit of talk of what work in progress. We're supposed to change this. I think I'll move that up to this part a little bit and say what we're doing at the end of this. The software that is required to do the exercises is AstroPy 0.4. The problem is there's a slight hitch in that 0.4 isn't out yet, so that may complicate it. We do have a release candidate, so that's what we're actually recommending what people use. And if you can't get the release candidate installed, that's not a problem. 0.3.2 will suffice for everything except the coordinates, and in that case, you'll see some differences in how things are being done. And that's a little bit later on, so there'll be time to try and get the release candidate installed. Part of this first part exercise thing is to make sure everybody has all the things they need installed properly and can run everything that they need to. So it requires NumPy, Matplotlib, Ipython. What we're recommending is the easiest way to install these things is Anaconda. And the default Anaconda that you'll download has the AstroPi 0.3.2. If you want to, you can update that by executing this conda command and get the release candidate installed. And so obviously the Ipython Notebook is sort of the basis for this tutorial material. Who isn't familiar with the Ipython Notebook? Okay, if you need help on, I'm not going to go into the details of, maybe I'll do a couple examples of what you can do here with the notebook. This link here, which is bit.ly, astropy-SciPy 2004, will download all the notebooks that we're using for the tutorial and the data files that are being used in the tutorials or as part of exercises. So if you download that, you should be able to execute everything that we're doing for the tutorial. Now, before I get onto the practical exercises, I'd say a little bit more of where things are going in AstroPi. Up to now, we've been focusing on sort of core libraries and things like that. One of the things we'd like to do is see more development of applications. A lot of that will go into affiliated packages. Some of them may show up in the core. I think we have a basis that's strong enough now to actually begin to develop a lot of useful functionality for applications themselves. There's still some more work to be done with WCS. So we sort of moved it from having a model and fitting package, and then having a WCS library that's a generalized WCS library that extends past what FITS provides. And that would be part of the basis of what the data, the ND data objects would provide in the way of being able to map array coordinates to world coordinates. And I'll let other people add a little bit to this, different things that are going on in current development. For this segment, the exercises are basically just to make sure that you can execute some things in the notebook. If you have any trouble doing that, please let one of us know and see if we can resolve the issue. Or if you have just trouble starting up the Ipython notebook, usually do that. If you have everything installed properly, you just say Ipython space notebook, and that should bring up, and you have to do that in the directory that the notebooks are sitting in. If you don't have any, it'll create, you can save them to that directory.
I'll just add to that. In Ipython 2.0, it's not necessary to start the notebook in the same directory, but we're recommending it anyways because a lot of the examples use paths to files that are relative to the notebooks. So those examples will just work the most smoothly if you're already, in that directory, same directory that the notebooks are in when you start Ipython.
Yeah, just to rehash that for the video, Ipython Notebook 2.0 will allow changing directories, but in order to make accessing the data easier, we're recommending you start from the notebook directory to begin with. And the second one is to create a new cell and try the various imports to see that everything is importing properly. And finally, actually executing something with using those libraries. This example basically opens a FITS file and uses matplotlib to display an image. So I'll leave these things up here. If you want to, who doesn't have the Ipython notebook running or doesn't have the software installed right now? You? Okay. Anybody else that needs help installing? Does everybody else have able to run the notebook? Who doesn't have Astropy installed or needs instructions on upgrading to the 0.4 release candidate? Okay, during the break, just let us, sort of wave us over to help sort those issues out. But otherwise, if you've got the notebook and up and running, you can start making sure that you can learn how to exercise things and execute things in cells, and that you can do these imports properly, and try a few commands to see if they're working okay. So at this point, we'll just start seeing if everybody can do what we need to do. Okay?
Do you want to have people print out the version of Astropy?
Oh, the version?
Vendor version?
Yeah. One thing you could do just to make sure is, if you were here, for example, just say, I think, yeah, you have to, that's what I was going to put in there. And then say print. Okay? Just to make sure you have the one we would prefer you to have. Okay. 0.2? How did we treat 3? Okay. Did you install
Sorry, oh, here it is. This bit.ly.
You can just do it in.
Or in one, and it's going to apply to all of your numbers.
No. Yeah, you don't need to do that.
And you're working together.
And if it still doesn't work, I'm more concerned that
Has the right version. Bit.ly, Astro Pi
that's
Documentation.
something we can fix. We'll fix it over. Again, it will work fine for all these portals, except for the last one. Okay.
I think I have it now. I had both of them. I had both the packages right here. I had the old one and the new one, so I did it myself.
Whichever. And Astro Pi done. That's good enough for now.
Okay.
And over the break, we'll try and get that upgraded.
Okay.
Now, what you want to do is start the notebook again, but from within the
Yes.
directory that has all the tutorial files. I still see a little bit of chatter, but is there anybody who is not able to get Astro Pi imported and have at least version 0.3? What about back there?
Why don't you start?
Okay. Yeah, we're getting, don't have a whole lot of time, so we'll start moving ahead. So units. Now, there are actually lots of different unit packages that have come out for Python. So one question we sometimes get is, why did AstroPy put its own in? Well, there are a couple reasons. I won't go into a whole lot of detail, but one is simply that we wanted a few features that none of the existing units packages had. This ranges from very basic things like just built-in support for common astronomical units to kind of more interesting things like automatic unit equivalencies. For example, if you want to be able to do unit conversions where wavelengths are treated as equivalent to frequencies, as a very basic example. And we did not actually start from scratch. We kind of did a survey of existing unit packages for Python that were out there, and the PyNbody project, which is a n-body physics simulator, graciously allowed us to sort of copy their unit library and iterate on it for our own needs. And providing a single unit package as part of AstroPy was also very important because this proliferation of unit libraries they don't all interact with each other perfectly. And we wanted to create this sort of nicely interlocking software ecosystem. And part of that involves having units that work across all the software. So we've been really making a lot of progress on integrating this unit support into all parts of AstroPy and the affiliated packages that use it, so that you get sort of consistent treatment of units across different pieces of software, different libraries that are using them. Really, really useful feature, it turns out. So I'm going to just kind of go through this notebook. The way I usually kind of like to do tutorials is actually to type things live and make it run, but we don't have a whole lot of time today and a lot to get through, so probably it's easiest for everybody to just click on these notebook cells and shift run them. But if you'd like to also try typing things in, that's fine too. Depends on your personal preferences. So to get started, the sort of idiom we usually use to use the units feature in AstroPy is we do this from AstroPy import units as you. Don't have to do that, but it's very convenient to just have this one very short letter to use to refer to all the units in the package. In principle, one could also import all of the units into their namespace, but that would be enormous clutter because there are dozens, maybe something like 100 units in here. So we usually just do import the units module from AstroPy as you, and that's sort of the easiest way to start accessing them via this variable now named u. And that's just a namespace that has all of the supported units defined in it, or at least all of the SI units. There are some other systems of units that can be loaded, but that aren't there by default because for the most part, you're not going to need teaspoons for your day-to-day work, but it's in there. So u.m is meters, and when you run that in the notebook, all you see when you type that is just the symbol for meters, m. Not terribly informative, but there you go. They do have other attributes, though, that tell you some more interesting things about them. They all have a doc string, which you can print out, and it tells you what u.m actually is. It's the base unit of length in SI. You can also ask u.m.physical type, and that tells you that it's length. And that's very useful when you're starting to kind of convert between units. All the units in AstroPy have some actual physical dimension associated with them that it strives to keep consistent. So you can't, for example, add a length to a mass, for example, unless you're using some kind of system of unit equivalencies, which we'll see how to do. Some other units that are defined are, for example, PC for parsecs, and like meters, it has a doc string, approximately 3.26 light years. We've got seconds. We have kilograms, and so on. There are quite a few, and in fact, I'm going to go ahead and click on this link that takes us to the Astropy Documentation, the comprehensive online documentation, and this is a list of actually all of the units that are defined in Astropy. You've got your angstroms, your fortnights. Yeah, there are quite a few. Also, we've got CGS units, ergs, dynes, even CGS EM units of various kinds, quite comprehensive, and it's not hard. We won't get into it today, but it's not terribly difficult to define your own units if, for example, you need something that's missing. And we're also usually happy to add new units to the core package as well. You can never have too many units. Now you can create composites of units using actual normal arithmetic. Are there any questions so far? Stop me. Feel free to just throw your hand up if there's any questions at any point. So you can create composites of units using normal arithmetic, the normal arithmetic operators in Python. For example, this will make a meter per kilogram per second square. And when you type that into the notebook, it will actually give you a nice sort of LaTeX representation of that. If you use the actual repr function around that predefined unit, or around that composite unit, it will show you that this actually creates a new unit object representing mass per, or meters per kilogram second squared. So all of these units, whether they're sort of predefined built-in units or composite units that you create yourself, are actually represented in Python as a class, an instance of a class called unit. So for example, if you are writing some function that takes a unit as an argument and you want to do type checking on it, you can always ask, is this variable an instance of unit? And it doesn't matter if it's a predefined unit or one that was sort of composited like this. So units by themselves can be sometimes useful, but they are most useful when they are combined with some actual value that you're attaching units to. And we call those quantities. And the quantity object is actually probably the thing that you see used most within Astro Pi by actually taking some value and attaching a unit to it. And there are a few ways to create quantities, but the most basic way is to just take a numeric value and multiply it by the unit you want to give it, just like you would on paper. So to create a quantity of 3 meters, for example, you simply enter 3 times meters, and you get a value of 3 meters. You can also make quantities from Numpy arrays, which is very useful. So if you import Numpy as NP as usual and create some array, this is just a 1D array. It could be a 2D array or an ND array. And just like we did with a scalar value, you can actually multiply a Numpy array by a unit. In this case, we're multiplying it by parsecs per year. And that returns a quantity with that array value, but with that unit. And that will allow us to actually do arithmetic between quantities that preserves the units and keeps them consistent. And that's what we will do in this next section. So quantities can be combined. Like before, define quantity 1 as 3 meters and quantity 2 as 5 centimeters per second per gram squared. And then if we take Q1 times Q2, it will actually kind of combine all of those units in a sensible way. So you get kind of 15 centimeters meters per second grams squared. Now, this centimeters meters is kind of redundant, but it's not, it doesn't necessarily assume that you want to sort of decompose those units. Sometimes there are reasons you might want to keep them separate, but we'll see later towards the end of this section that you can sort of take a quantity with units like this and say, oh, kind of collapse this down so it's maybe sort of converted to just meters squared
for example, in the numerator. Well, here's one example of that. You can actually take a quantity that has some units and convert it to different units, as long as that conversion is physically consistent and valid. So here we're taking the 15 centimeters meters per second gram squared and converting it to meters squared per kilogram squared per second. And that will actually return, okay, now it gets rid of the centimeters meters and you get meters squared, and the value out front is converted properly. Yes?
How does that work under the hood? Say you had a really large array and you run out, you barely have enough memory. Does it make a copy, or is it a view?
For a very large array, it will actually create a view of that array and just basically puts quantity around it and attaches the units to it. There are, I won't get into detail on this right now, there are some kind of tricky things involved when you start doing arithmetic on quantities. We've got it to the point where it's usually going to be pretty good. And when NumPy, I think 1.8 or 1.9 comes out, and everybody is on that, it'll be even better. So, but yeah, in general, if you take some existing array and convert it to a quantity, it's a pretty immediate operation. No copying happens. Okay. Just one other sort of small point about quantity objects. If you have a quantity like here, 5 parsecs, you can access the actual numeric value simply via the dot value attribute, which will just give you 5.0 with the unit stripped off. For arrays, that's the same deal. If you have an array quantity, the dot value attribute will just return a pure unadorned NumPy ND array. And you can also just access the unit by itself using the dot unit attribute. Advanced features, I kind of mentioned this earlier. You can decompose units. So here we have a unit that's like 3 centimeters parsecs per grams per year squared. And when we take a unit like this and called the dot decompose method, that will take this sort of more complicated unit and automatically convert this centimeters times parsecs to just meters. There are some sort of rules for how that works. We don't have time to go into the details, but basically when it's parsing the units, it will see centimeters first and well, it actually, I believe it actually decomposes automatically by what your default unit system is, which is SI. So it will say the centimeters in parsecs, that's the unit of length, and it'll say, okay, what's the base unit of length in SI, and it'll take meters and just sort of combine that all of the sort of length values, units in that compound unit into meters, and scale everything appropriately. But you can decompose to other bases, and in fact, if you look under the units module, there's a .cgs object, as there is also a .si object, and you can ask what are sort of the base units that define the CGS system of units, and it'll tell you, well, you've got basically grams, centimeters, seconds, and there are a few other units we have to put in here for consistency, like kelvins. So you can take that same previous unit, centimeters, parsecs, with grams and seconds, and decompose that to CGS bases, and now you get a value that's in centimeters squared with grams and seconds, whereas previously for the default, which is SI, it gave meters and kilograms as sort of the base units. You can also convert between systems of units. So this is, again, that same unit, and just ask it, what is your value, what is your sort of equivalent in CGS-based units? And that will actually kind of combine everything up, and it recognizes that, oh, this is some value of energy, so let's convert it to ergs, and then it's got grams in the denominator. So there's a lot of things that it does sort of intelligently like that. One last example, and then we'll get down to equivalencies and some exercises. Physical constants. There are a myriad of useful physical constants for astronomy that are predefined in AstroPy. All of the constants come along with useful information about them. For example, I'm going to, from astropy.constants, import G. I'm going to actually insert one little slide here. If you print G, it tells you some things about it. It tells you what it is, the gravitational constant, tells you its value, the known error on this particular value for the constant, and also gives where we actually got that value, in this case CO data 2010. And that information is available for all of the constants that are defined in AstroPy. So we could do an example here, for example, like compute the gravitational force on a 100 kilogram satellite orbiting the sun at a distance of 3.2 AU. And so we would actually just use Newton's laws here and take G times 1 solar mass. Mass of sun is defined as a constant, but it's also provided as a unit of solar mass. So we could actually do constants.msun, or in this case u.msun, times 100 kilograms divided by 3.2 AU squared. And you just type that out, and it will give us the force felt by that satellite in kind of ugly-looking units, meters cubed, solar mass, AU squared. But we could take that and convert it to newtons because we just want the force, and it'll tell us exactly that value in newtons.
Can I ask a question?
Sure.
How is that different than the few lines above when you just had the CGS and it did the same thing? So how does that
So the two method can convert to any units that are physically consistent. I could do 2 newtons, I could do any other sort of, I could do kilograms, meters per second, meters second squared. Whereas in the above example where we were playing with the bases, that just kind of converts to the base units of that system of units. So it's going to stick to always kilograms, for SI, kilograms, meters. For CGS, it's always going to convert to centimeters for whenever it finds the length. It's sort of a default basis. Couple more things. Equivalencies, this is sort of one of the key features that we wanted to add for AstroPy. Normally, if you try to do something like this, here we're taking a value in nanometers and trying to convert it to gigahertz. And you will get this long, unhappy-looking trace back at the bottom of which it tells you unit error, nanometers, which are a unit of length, and gigahertz and frequency are not convertible. And the answer to that is when you do the call the to method, you pass in this argument equivalencies. And there are a whole bunch of different equivalencies that are defined in AstroPy. Don't have time to go through them all, but this is one of the most common is u.spectral. The reason you have to call it here is sort of an internal detail, but equivalencies can, some types of equivalencies can take arguments to them as well. In this case, it basically means treat length and frequency equivalently, and it has the conversion factors between frequency and wavelength via, I don't know, C already predefined. So it will actually just take 450 nanometers and convert it to the correct frequency in gigahertz. Likewise, you can take a value in electron volts, and again, it will know how to convert that energy to the associated wavelength. And this is a somewhat more complicated example, but here there's also a spectral density equivalency, and you can sort of take this quantity in ergs per centimeter squared per second per angstroms, and get the associated equivalency in Janskis. So don't have time to go into all the details on that, but you can look that up in the units documentation. Okay. One last thing. This is kind of where a lot of the power comes in, is that we've actually made it so that a lot of the built-in functions in Numpy understand what to do with quantities. So you can ask, for example, what is the sine of 30 degrees? I think normally the sine function in Numpy requires values in radians, but if we tell it, here's some value in degrees, it will actually correctly tell us, for example, the sine of 30 degrees is 0.5. Likewise, if we pass in something like kilometers, value with kilometers squared, and ask for the square root, it will give 10 kilometers. So all of these functions will actually work properly on the units as well. Exponentials require dimensionless units. So in this case, we've got meters divided by kilometers, which is ultimately going to be dimensionless. So the exponential will work properly on that. One thing that needs to be looked out for here is that if you just pass in some numerical value without a unit, arcsine, for example, is not going to magically return a quantity to you. If you don't use quantities sort of end to end, Numpy doesn't magically know how to return a quantity. So if I ask for the arcsine of 1.0, it's going to give me the correct numerical value, but there's no units attached. However, there is this kind of special unit built into Astropy called dimensionless _ unscaled. I believe we actually recently added in a slightly nicer to use alias for that. It's just 1, right? I believe that's new though, so don't try it if you don't have Astropy 0.4. This is basically saying this is a unit of 1. And if we pass that into the arcsine function, then it actually will return us a quantity in radians. But if we wanted the result in degrees, we would basically take that radians quantity returned and convert it to degree. And so you get 90 degrees out for 1. Okay, any questions on that before we take a few minutes for the exercises? We'll just spend, most of these exercises are, I think, fairly easy. We won't spend a whole lot of time working on them, but you can either read this on your own and start hacking away, or I will read them off as well. The first is, what is 1 barn megaparsecs in teaspoons? Barn's a unit of area, and megaparsecs is a unit of length, and teaspoon's a unit of volume, so you should get some dimensionless quantity from that conversion. Just a scale, basically. The second exercise, if you get that working, is what is 3 nanometers squared megaparsecs per meters cubed in dimensionless units. Fairly similar to the previous example, but a little more complicated just in terms of the arithmetic. And finally, this one you'll have to use equivalencies. The level 3 example is try and use equivalencies to find the Doppler shifted wavelength at a line of 454.4 nanometers if the object is moving at a velocity of 510 kilometers per second. So if you click on this link, there's actually a list of the available equivalencies in AstroPy, and I believe for that one you'll want to use probably these ones, right? So yeah, I think so. The Doppler shifted equivalencies. So go ahead and give those a try for a few minutes, and we'll walk around and provide help if you need it, and in maybe like 5 or 10 minutes, I'll go quickly over the solutions.
Yeah, one of the things I forgot to mention is that we generally put more exercises than most people can get done, so don't feel bad if you don't get through all of them every time.
Right, that's why it's level 1, level 2, and level 3. If you don't get to level 3, that's okay, because if this is all new to you to using AstroPy, then that's fine, if you can even get level 1 done. And also, you've all got the solutions in the notebooks directory that you downloaded. Each of these has a separate notebook that has solutions in the name, so don't fret. Feel free to also raise your hand if you have a problem with any of the exercises, and people will be around to help.
I'd say you went like 8 minutes over. Yeah. I wasn't sure what to do. Jump up in the all screen. Throw it all in. What's that? I'm not trying to figure out how we're supposed to. What's the idea? If you give me an Apple one.
So I got one question that deserves to be addressed. I was asked, how do you get megaparsecs? For most like standard SI and kind of CGS units, all of the standard SI unit prefixes will work too. So if you have u.pc for parsecs, you can also just do u.mpc for megaparsecs, for example. Just like with nanometers, meters, all of those will work. So it seems like most people have at least gotten through the first two exercises and are at least a chunk of the way into the third one. So in the interest of time, I'm going to go through these solutions really quick. I think a lot of people seem to get this just fine. So from astropy.units, import Imperial. And this is a module that has all the Imperial units defined in it. And then you can just type 1 barn, which is a very small unit, times MPC, which is a very large unit. And just, you could either save that to a variable, which I saw some people do, or just bracket the whole expression and do 2 imperial dot teaspoons. Okay. You could also take this whole thing and just divide it by imperial.teaspoon and get sort of a dimensionless, or I think you have to do decompose on that then. Yeah. There we go. And then you get sort of just a scale quantity. So actually, that's sort of what you would do in the level 2 example. 3 nanometers squared times MPC divided by meters cubed, and then just decompose that. Oops. An alternative, U dot nanometers. An alternative to that is again, you could also do 2 U dot dimensionless unscaled, or if you have Astropy 0.4, you could do 2 U dot 1. Level 3, so here you would actually use the Doppler optical equivalency. And the way you would do this is, so it's object is moving 510 kilometers per second. Kilometers per U dot seconds. And you want to convert this to wavelength, the Doppler shifted wavelength. So nanometers. Now again, this is not going to work automatically because it doesn't know kind of how you want to scale this, how you want to actually treat velocity and distance equivalently. But you can provide this Doppler optical equivalency, and you tell it I want the equivalent Doppler shifted wavelength at a line of 454.4 nanometers. And if you read about that in the documentation, it tells you kind of more about how that works. Gives you all the formulas that it's using to do the conversion. Okay? So if there are any other burning questions, we can maybe hold those until the break. And I'm going to turn things over to Tom to talk about tables.
All right. Let's see. Okay, so the next aspect of the tutorial, as Eric mentioned, is tables. Tables are basically things that you'll encounter all the time, like a spreadsheet of data or a table that you'll see in a journal with columns of data and rows of data. So the AstroPy table class provides basically a way of dealing with this heterogeneous tables of data. This is basically a wrapper or superset of the functionality that you get in the Numpy structured array. But the goal of AstroPi is actually to make it a lot more convenient and a lot easier to deal with these data. And one of the key things that the AstroPi table brings to this show is making those tables mutable easily. And by that I mean it becomes easy to add rows of data or add columns of data to your tables in a way that is possible with NumPy, but it's not very easy or handy for users. So I just give a list here of some of the main features that are in AstroPi table. Make it very easy to initialize a table from a wide variety of data structures. And like I said, the tables are mutable and you can do all kinds of nice things with them. One of the things tables does is it sort of it integrates the handling of missing value data, so that in NumPy you have these masked arrays which are separate from the normal structured arrays. With AstroPi, those two sort of interfaces are unified, so it looks a lot more similar when you're dealing with a table that has missing data, which can often be important. The other thing AstroPi table brings to the show is the addition of metadata, which is very common and important in astronomical tables. And by that I mean, if you think about your fits table with all of the header keywords and other information, or you talk about table columns having units or descriptions or other sort of data attached to them. And so that's one of the key things that we're providing support for in order to make table the sort of container class that you can use to sort of fully represent some of the files that you'll commonly encounter. The other thing is, I'll sort of skip into this, but the AstroPi table starts bringing some high-level functionality, sort of a database-like functionality where you can do table joins and merges and so on. I won't talk too much. You may be familiar with this package called Pandas, which provides a data frame class, and that is a very, very powerful high-performance package, and you might ask, why aren't we just using that as the base table for AstroPi? And unfortunately, there's a key blocker, which is basically that Pandas doesn't support multi-dimensional columns, and that's the kind of thing that actually you find relatively frequently in astronomy, like the Chandra response function is represented, where you actually have an array as each element of a column. And so that's just, it's a little bit of a bummer, but we kind of went off in our own direction in the way that happens. So I give here the link of where you can find all the full documentation, and there's a lot. So let's just jump right in. The first thing that you would need to do is basically just import, and the canonical statement that you need to use here is this from astropy.table import table. I'm also importing NumPy in the standard way. So the first thing you need to do is create a table. And like I said, there are a whole bunch of ways of creating a table with the AstroPi table. You can read a table or from a file, or use a web URL even. So it's kind of handy if you have a link for some table that's from a web page, you can just read that in. You can create a bare table and just start adding columns one by one, or add rows of data one by one. Those are not the best for performance, and so if you actually have all the data at the beginning, you should just create a table with all that data at once. So there's there's the documentation basically tells all the gory details and provides plenty of examples, but let's just start with the very simplest, which is essentially creating an empty table and then adding two columns of data. One is name and flux, and so this is sort of representing some observations of some sources. And you see that hasn't actually produced any output, and in order to look at the table, we need to print it. And so you see that in Ipython Notebook, when you actually just print the variable name or put the variable name into a cell and run it, that produces a nice little HTML table rendering. If you did this in a terminal session, what you get isn't quite as pretty, and the example here shows what you would see, which is more like the NumPy representation of tables, where you're getting this tuples showing the row values for each case, and then a sort of raw representation of the D types. In a notebook or in a terminal, you frequently can use print. And this is how it would look if you're just running from the console window, and that also gives a sort of a nice human-readable formatted version of the table. So there are a whole bunch of attributes that you can look at from the table, but I'll just focus first. If you get a table, you have the column names handy enough, and then it is frequently important to know the raw data types that you have inside the table, and so this shows that you have a column called name, which is an 8-character long string, and you have a column called flux, which is a floating point, an 8-byte, sorry, did I say bits? Byte floating point. So next thing we need to do is talk about accessing parts of the table. I mean, that's sort of what the real reason for having them. So the first thing is we want to just look at the flux column. So one of the, let's see, this doesn't have, well, there aren't any meta attributes defined in this case, but you see that there's space for them. So we have this column named flux, and it has a potential unit. It's got a format descriptor, which we'll get to later, and also a description, which is sort of the high-level textual description. So the important thing is just that those attributes are there and can be used, and in some of the table reader applications that we'll see later, those do actually get filled in. So that's given us all of the values as a single array, and you notice that this is actually returning what's called a column object, which is, it's basically derived from the Numpy array. And so if you look at this column object in detail, it looks more or less like a regular Numpy array, but it's got this extra stuff on top of it that makes it a little bit handier. So we can, of course, access row 1 of this flux column. So we got that's the second value here, the 2.2. You can also access a row of data by selecting with index 1 on the table. And again, similarly to column, you have this object, which is a table row, which itself has some metadata built into it. So this is all sort of, it's integrated, it's sitting on top of Numpy, but it makes things a little bit handier and more friendly to use. Likewise, if you select first a row, you can then from that row select a particular column. So it's just kind of turning this syntax from this one backwards. Here we were selecting a column and then asking for the first row of that. Now we're looking for the flux column of the first row, and obviously you get the same value. Slicing is an important feature. So in this case, we've asked for rows 1 and 2 out of the table, and that returns a new table. And nice thing is, all of the meta attributes and everything else associated with that table are copied over. Now, when you do a slice, it's not actually copying, it's a view of the table, which is important for performance. The other interesting thing you can do is the so-called fancy indexing, where we want to select rows 1 and 3. So if you're familiar with Numpy handling, it's all should be very familiar and comfortable to you. So I want to emphasize next one of the key and powerful concepts that you should be using all of the time when handling tables, and in fact Numpy arrays and so forth, which is the Boolean selection masks. So here we're going to try to make a new table which consists of all of the objects that have a flux greater than 3.0. And then we're going to make a new table which is created by applying that mask to the original table. And you see that indeed we've made a new table with only the high flux sources. And this is a very powerful concept that you should be using all of the time in your analysis. So I mentioned that one of the powerful features of the Astropy table is that there are a lot of ways to modify the tables in place, and that's something that's hard to do with Numpy structured arrays, but it's quite easy here. So first thing we're going to do is add a new row to the table. So that's done with this line, pretty simple add row. And the inside of this is just a tuple that has each of the values corresponding to the columns in that row. And so we need to give it a new name and a new flux value. And the second thing I'm going to do is create a new column, which is actually the log of the flux created by this arithmetic expression, the log 10 of the flux column. So you see that we got a new source, this one, source 5, and now we have the log flux. So that's pretty good, and you have this very easy syntax here, which makes it look like sort of a Python dictionary, but in fact that just adds on this new column at the end. There's also a method called insert column if you want to make a new column, but you care about where it's placed. You don't want to have it at the end of the list of columns. So, let's see, you can't easily insert a row in the middle, I think. No. That's actually, maybe that's a feature request. Do we have, yeah, right now it's just adding rows at the end. I suppose you could jump through some hoops. Tom's going to write an issue on that right now.
That's a tricky one to do, though.
Well, you'd add a row and then shift everything down.
Yeah. You know, it's important to point out again that the operations which are doing this mutability, that are actually modifying the table in place, are somewhat expensive in terms of memory. Excuse me. So you don't really want to do them all the time if you don't have to. Okay. Sorry. Sorry, I just have a little, where were we? Add row. Log flux, modifying the table. So, where were we? So we were talking about the setting up the formatting here. There's a lot of digits here that we don't really need. And you can make things prettier with this T flux, or sorry, by setting the format. And so this is just typical. Sorry about that. I'm just not feeling well for a second. Okay. So using the sort of normal Python sprintf format, you can tell the table how to print itself. And so you see that, voila, somehow I care a lot about making things pretty, and so the table knows how to make a pretty representation of itself. So sometimes, of course, you have an AstroPy table, and it may not be what you want, and you want just a plain old Numpy array, and so you can convert it with Numpy array. And this is important because it's important to note here that the Numpy array actually makes a copy of the data. And so, again, if you compare or are worried about performance, this will make a copy in memory. If you want to, you can specify false here, and it appears to have done the same thing, but in fact, the array that you get out is a view of the original memory. And so if you change the elements in the table, then the elements in this Numpy array would also have changed. So the next thing that I mentioned earlier was that mass tables, AstroPy has support for mass tables. And what that means is that if you have missing values, which are where you simply don't have data or it's known to be bad data, those can easily be represented. And the way that you do that with AstroPy tables is with this flag called masked equals true, which tells it to make a masked table. So I'm going to make a new table, which is masked. Oops. And you see that so far it just looks like a regular table because there aren't any missing values to find. But I can actually set the mask now, which says that a value is bad here. And so you see what comes out now is that we have this dash dash representation. And that basically underneath the hood we're using a masked array. And the way that you use that, if you there are NumPy operations which will respect those masking, but mostly a lot of times you just want to put in like a fill value here, and that if you're, say, putting this off to a table for publication, you could also, when you're writing this out, we'll see an Ascii table. There are ways that you could fill in these mask values with a ... for making a LaTeX table for publication. So the last thing I want to go into a little bit is high-level table operations. I mentioned earlier that AstroPy has a lot of these high-level table operations like grouping, which basically lets you perform things like, say you have a data set and you want to take the daily mean. So you've got a whole bunch of photometry or something taken at regular intervals, and you want to take the daily mean. Stacking vertically and horizontally, that basically lets you take tables and merge them either left and right or like this, or do database style joins. So let's just take a quick look at this. So the first thing you can do is just with this join AstroPy table. So this is our original table. Let's see. Now what I want to do is imagine that you have another table which has flux values, additional flux values from a different reference, but maybe for some of those sources overlapping. So we have new table there. And what I want to do is make a master table of flux measurements which are joined and matching the values joined based on this name value. So this includes every row from each of the tables, and this is called an outer join. So what did we get here when I ran this? Don't worry about this warning. This is a funny that I have to understand still just when running an Ipython notebook. But basically, I took this table, which has source 1, 2, 3, 4, and the flux. Okay, and I joined it with our new table. Actually, let me print that out like this. So we have, say, source 3, notice, has a value of 3.5 for flux 2 and 3.1 here. So we did an outer join, and we get finally this source 3 line with the flux and a flux 2. Where there's no data there, you just have missing values that have been inserted. And now the real power of this is that we can get the mean now of the flux 2, and notice that when you have missing values, it actually just takes the mean of the available values, which is a good thing. So one of the other things we could do is say that we're just interested in a table where we have flux values for all of the available values, and we don't want to have any of these missing values put in. So that's what we see here. So the very last thing before we jump into the exercises, and I actually made in a little bit of time, is that the table object actually has this unified I/O layer, which lets you conveniently take your tables and write them out into different formats. And so let's say that we have our table T3 now, and we want to write that out as fits. You can just go do that with that command line, and it's quite easy. Likewise, I can write it out as a VO table, and I suppose I could actually go ahead and print that. I could do cat test.vot, And you see we got this VO table out. And likewise, you can read that back, and you see that we've read that, or we've written that table out to fits just with one easy command, and we can read it back, and we get the values expected. So the exercises that we've set up here, they actually go pretty deep, and it's sort of, there's enough there for ninja table people to hopefully chew on. So what I want you to do is actually do the sort of practical exercise of handling a couple of tables that come from the Chandra source catalog, and we're going to analyze the properties of sources from a series of 21 observations. And don't get too intimidated by this. There's a lot of material at the front, but actually the answers are fairly straightforward. And so, really, the first thing that you want to do, which I've given you the answer for, is reading in these two tables. And so that was completed. So what we have is the two tables. There's a master sources list and an ob sources. The ob sources is actually a record of every source that's been detected in a Chandra observation, and then the master sources is where they've correlated those sources over different observations. And so I'm not actually going to read through all of these exercises. I think we can just break off, and you can start reading these. And like I said, don't worry about too much about all of the details of all these columns and so forth. What we need to do is just jump into this and start trying to explore those data sets via tables. Right? Okay, well, I think I'm just going to go through some of the solutions now, and the solutions here are a little bit longer, so I'm actually just going to go through the solution notebook. So again, the first thing that we would have wanted to do is our imports. Okay, and as mentioned, and actually in the original part, we have to import table, and then we read those data sources. Okay, so as far as exploring, for displaying, that's pretty straightforward. You just type the name of the variable that you use for defining those. And one of the things that you see here is that we have this middle column with the dashes or the dots. And what's happening here is that Astropy table by default doesn't want to create these huge long tables that could fill up memory if you happen to read in a billion row long file. So you also have the ob sources, and that's interesting. I don't know if we have. I put in a pull request to fix this. Why we're getting those dots in the middle. May not be running the right version. In any case, the next exercise was to just look at the column names, and that again is pretty straightforward with the column names attribute. We wanted to look at the length of these tables, and just like a Numpy table or most Python objects that have a length, you can get the length with the length function. And finally, we can look at the data types. So the next exercise, as I mentioned above, was getting the notebook to actually print all of the lines of your table. And the way you do that is using the pprint method. And so that basically has a couple of parameters, the max lines and the max width, and it lets you format the table within the confines of your available screen, or if you want to see everything, you give it max lines equals -1, which is just a sentinel to say don't apply any length limit. And so you see now we get something that has all of the table columns, and table rows rather, but it's a little bit long. Okay. Modifying the tables, we wanted to remove one of the columns, rename a column, and add a new column. So we have a remove column method, and that is pretty straightforward. So if I actually look at the, oh, this isn't going to work now. I need a new cell. You see that OB column went away. We can rename the column with the rename column method, pretty straightforward. And finally, we can do this computation. There was some discussion about whether the units of these values actually get propagated correctly, and that's a feature that's coming in Astropy 1.0, but it isn't there yet. We're going to have better integration between the quantities that Eric talked about and tables, where tables will be able to represent a quantity column in a way that should all just work naturally and intuitively in the way that you would imagine. Finally, we can now look at the column names and confirm that we do have this new rate value, and that the GTI obs column has been renamed to obstate, and that OB went away. All right. So now looking at this observation source data, we wanted to use the histogram function to actually make a histogram of these values. And the solution there is that we just select out our ob sources, the flux aperture B. I'm going to make some bins. And then the next thing is we're going to use this Boolean masking to define a mask, which I often use the word OK for that. And then plot again, overplot a new table, or rather a new column, which has only those OK values selected. And so you get this histogram here with the main set of flux values, and then the subset. Now we get into the fancy stuff where we're doing a join of these table columns, and so we just import join. Then the simple thing is that we're just doing a join on the master sources and the ob sources, and by default that joins on any common table columns, which in this case the only common table column was this MSID attribute, the master source ID. And I'm going to do that, and I'll show you that the length of this new sources is actually a subset of the ob sources, because not all of the ob sources had counterparts in this master sources list. Okay, so the last thing we're going to do is, that's not good. From Astropy coordinates import sky, oh, we must not be on Astropy 0.4. Don't know how that happened. But I think that we'll just going to skip that for now then. So the last part was to look at the grouped properties of sources. And so this is what I mentioned, the sort of powerful kind of database-driven technology that you can use. And the first thing we want to do is look at this create a new table which is grouped by the MSID key using the group by. Pretty straightforward. And then I'm going to use the difference method to determine how many sources are in each of these groups. What that means physically is there were multiple observations of sources with Chandra, and this catalog identifies a unique identifier to each unique source on the sky called MSID, and we've made a new table where those are grouped by that MSID, and so this is going to tell us how many times Chandra detected each individual source. And so you see that a lot of them were only seen once, but a lot of the sources in this catalog have at least up to 21 observations. And now I'm just going to show you in detail one of those, and this is the 50th group. So this is, there's nothing special about 50, but what it tells you is that this particular source was seen 5 different times by Chandra.
Question on the grouping to make sure I understand. So what it's doing when you do the group by method, it's looking for everything with the same MSID number, and then literally rearranging the table so that those rows are next to each other?
Yep,
and
exactly.
Any which have the same MSID get called a group, and so there might be a large number of rows but a smaller number of groups?
Yeah, exactly. So finally, to bring this home, you can do the aggregate function of the groups in order to find the mean within each one of those groups. So the mean flux, or actually the mean value for all columns, where that's appropriate for each one of those groups. This cannot aggregate. Sorry, I didn't set this up, Eric. We must be on the wrong version of Astropy. Cannot. Oh, wait. Sorry. These warnings are actually expected, and what this means is that these are all. Well, let's see. RA deck, you should be able to aggregate. Did we get a table?
Maybe the RA deck are string.
Are there string value? Oh, sorry, you're right. Yeah. What is telling you here is that the RA and deck in this table is actually a string. We didn't turn that into a numeric value, and so it's just giving you a warning for anything that it can't apply the mean function to. So what we ended up with is a table where we do have means for each one of these, and now you see in this table that each MSID is unique, and we have mean values. And finally, we can rejoin this with master sources, and come up with the unique name and other values, including the RA and DEC, for that particular MSID. So kind of blew through that pretty quickly. There's a lot, but I recommend that you go read the documentation and start using some of this because there's a lot of power there. Yeah.
Sorry, one other question to clarify. Back to the join. When we did the inner join, the reason we got fewer elements in sources than in ob sources is that some of the MSIDs in the ob sources didn't exist in the master sources, so it basically filtered those out. Is that right?
Yeah. I mean, you basically have a mismatch. You might have some things in ob source that are not in master source or vice versa. So it only puts things into the final table that exist in both, as opposed to an outer join where it would have a row for every single value in master sources and a row corresponding to each value in ob sources. All right.
So we'll break for 15 minutes now.
And if there was anybody who didn't have AstroPy 0.4 installed, let me know and I can, and I or someone else can help you do that. Go take your break first. There's coffee out there, snacks. Take care of yourself first, and then we'll work on getting the latest version installed.
I think I have the not latest.
Right. So when you come back, we can
Okay.
look at that. All right. I probably don't need to ask this, but is there anybody who's not familiar with the basic format of FITS files? Okay. Just making sure I don't have to really go over that. I guess another sort of follow-up question to that is, raise your hand if you have already used PyFits before. Okay, great. That makes things somewhat easy. So the FITS handling module in AstroPy is called astropy.io.fits, and it basically right now is PyFits. It's just PyFits has been ported into AstroPy, and we're sort of making progress on integrating its functionality better into the other sub packages of AstroPy. For example, this doesn't work yet, but in a near future release, you'll be able to, for example, if a keyword in a header has some unit in the comment, described in the comment, as long as it's in the standard format, the value you'll get back will be one of the quantities we discussed earlier that has the appropriate units attached to it. That's sort of an example of where things are going in terms of integration. The example data that is provided is this gamma ray sky background used for the large area telescope instrument of the Fermi telescope. To open this file, you just enter from astropy.io import fits. The IO module, which you'll see more of today, is kind of where we've put all of the file format handling. Something that some people do if they have old codes that already use PyFits is you can just import fits as PyFits, and that will generally work. But for new code, we recommend getting rid of the PyFits and just calling it fits. That's a lot more straightforward. And to open a fits file, you just type fits.open and provide the path to the fits file. So if you're in the notebooks directory and you have this data file, that should work. If you get an exception, then you're just basically probably in the wrong directory. And you can find out about, kind of get an overview of what's in a fits file by calling this HDU list object that's returned from fits.open. You can call its .info method. And that tells you some things about what's in this fits file. It has two HDUs, two header data units. The primary HDU, which is always in there, always in a fits file. And this tells you that it's an image, it's actually an image cube with 30 slices of 720 by 360 pixel images. And it also has a table in it. The table contains just one column, actually. This format means 30 rows by one column, and there's just one column of double precision floating point values. This is using the actual fits format for column types, so capital D is doubles. We won't do much with the tables today. We're going to focus mostly on images. To access the primary HDU, which contains this image cube, you just use the sort of Python indexing notation. So this HDU list is actually basically a Python list. It's a special class called HDU list, but it otherwise works equivalently to a Python list. So to get the first HDU, you just index it with 0. That might be a contrast. If you haven't used PyFits before, that might be a contrast to with your expectations, because a lot of older FITS-related tools use one-based indexing, as in Fortran. So sometimes if you're like in IRAF or something, to get the primary HDU, you would use 1, not 0. But everything in PyFits is 0-indexed, 0-based indexing, so that's something to be aware of. And that goes for like image coordinates and things of that nature too. So we can save off the first HDU from the HDU list. And actually, I'm going to just show you. This doesn't really tell you anything very interesting right now if you print it out, but it does tell you that what you get back here is this primary HDU object. So HDUs have two important attributes. There aren't too many others that you usually would access. The first is the .data attribute, which this says which behaves like a Numpy array, but actually it is a Numpy array. There's no difference. It just is a plain Numpy array for images. This is another example of where more integration with Astro Pi is going to happen. Eventually, this will return one of the more advanced ND data objects, but right now it's just like in PyFits, you get a ND array. And so, like, for example, you can ask about its shape. This is another one of those kind of Fortran and Fits world versus Python world issues is axes, right? When we looked at the basic dimensions, this actually prints it kind of in the standard Fits format where, for example, the number of columns is given first, and the number of, like, this is basically X, Y, Z. So, but in NumPy, the axes are usually specified the other way around by default. So the array you get back is not 720 by 360 by 30, but rather 30 slices by 360 rows by 720 columns. So that's also important to be aware of whenever you're pulling these objects out and plotting them and doing what have you. The other important attribute on HDUs is the header. And if you just type hdu.header without a print statement or anything like that, that simply displays the entire contents of the header. And depending on the width of your screen, this may look nice or it may look kind of ugly because the comments might run off to the other row. But that just shows you the entire Fits header. It doesn't do anything to summarize it or anything like that. It's just exactly as it appears in the file. So an important thing to be aware of about the header object is it's a kind of tricky, interesting object. It, for the most part, works exactly like a Python dictionary, but it's an ordered dictionary. All of the keywords are stored in a specific order. If you're opening an existing header, for example, the keywords have an order associated with them that is exactly its order in the header. So when, for example, you're adding new keywords to the header, you have to be, if you do something like this, for example, if it was like a new keyword and you wanted to just add it to the header as if it was a dictionary, the default is they just get appended to the bottom. But there are some other options for inserting new keywords into specific locations that we'll see. But for the most part, you can just think of it like a dictionary. So if you want the value of the telescope keyword, or telescope as it were, you just use the square brackets notation, just like a dictionary, and it returns a value. It doesn't return the comment because most of the time we're just interested in the value. You can get to the comments, however, using the header.comments, and that also just works like a dictionary. So we can ask what the comment is for telescope. Sometimes people ask about that. Apparently this one doesn't even have a comment, so you just get an empty string. We could also ask what is the instrument or instrument, and it's the large area telescope. And say we wanted to plot for example, the first slice in the image cube. So we would just use hdu.data, 0 for the first slice, and then comma, colon, colon to just take all of the image. Or in standard NumPy notation, you could also write this ... to just say, give me the remaining axes. And this bit is important, origin equals lower. This is usually useful when plotting images from FITS files, because this goes back to that whole axes ordering thing, and like not just the order of the axes, but also the way they're oriented, because the top right, the top left is basically 0, 0, but when you're plotting that, you kind of want that to be treated as like the x and y coordinates on just like sort of a standard Cartesian axis. So you would kind of, when you say origin equals lower, that sort of flips it so that the origin is at the right location. And I did not start Ipython with the PyLab flag, so that didn't work by default. matplotlib.pyplot as plt, and that should display a slice of that image. Okay. So assigning two headers is, again, just like a Python dictionary. So like originally we saw that the telescope was glassed. That's actually the old name of this telescope, the Gamma Ray Large Area Space Telescope. And we want to update it to its new name, the Fermi Gamma Ray Space Telescope. So again, we just assign that directly to the keyword. And since that keyword was already in the header, it will just update the value in place. It doesn't move its position in the header. It keeps its original position. But when we add a new keyword, for example, this modified keyword, and this is actually the old version of this notebook. I thought did you do something with the files or anything?
Oh, I restarted it, but I may have restarted in the wrong directory.
Mm.
When you started it with the old 0.3.2 Astro Pi.
Okay, no matter. The reason I bring that up is because this is actually the wrong date format for what you should use in FITS keywords. The standard format is actually this kind of thing, 24 year dash month dash day. So if you put a modified keyword, that's sort of the date format you should use. Not that AstroPy cares. To AstroPy, it doesn't have any specific knowledge about the semantics of most of these keywords. It's just a key value pair. But if I'm going to be correct about it, that's sort of the format to use for dates and FITS files, by standard anyways. Of course, with FITS there are all kinds of conventions. And we can also update the data in place. Now this is actually kind of an important point I want to make about a lot of people who I've seen using PyFits in the past and AstroPy. Here we want to just, in this example, we're replacing the .data attribute with a slice of the data, of like the first slice of the image data. A point I like to try to make often is that the FITS module will try to be smart for you about how the FITS file is formatted. You don't have to sit there and like manually specify, for example, all the n-axis keywords to make sure that they're correct to match the data. What the FITS module will do for you is, if I update the data, here I'm replacing a data cube with just a single slice of that data cube. It will automatically replace all of the header keywords that are relevant to actually correctly specifying the data in the file. So it does know about certain keywords that are important to the data structure. And just to drive that point home, I'm going to scroll up a little bit and show where I printed out the header. Here it has n-axis 1, n-axis 2, n-axis 3. But when I replace the data attribute with this slice, and if I print the header out now, it just shows the n-axis 1 and n-axis 2, and it deleted the n-axis 3 keyword and updated the n-axis keyword to 2. Although, one thing I want to be clear about here is that currently the FITS module only knows about very basic things like that. It does not know, for example, about how to handle FITS WCS keywords, which is an important point to make. And you can see here that we do, in this file, have some WCS for like the third axis. Tells us that it represents photon energy, and it's got some units and things like that. So when we took just a single slice of that at a single level, we also want to remove all of these WCS related keywords for the third axis. So to do that, you can just do hdu.header.remove and then give the keyword and just run that for all of them. If you run it a second time, you're going to get a key error because you've already removed that keyword. Another option, which I didn't show here, because the header works exactly like a Python dictionary, if you're familiar with it, you can also use the standard del keyword. So you can also do del hdu.header and then just give the keyword name. That will also remove that keyword from the header. If I run this now, though, it will tell me that that keyword was already deleted. So two options there. And now we can basically take that slice. We already updated the data attribute and updated the header, and write that out to a new file. So you just do hdu.write_to and give it a file name, and it does that. And this clobber equals true is the same as overwrite. Just overwrite the file if it already exists. And if you actually ran this twice, you would see a warning like this. Likewise, this is just writing out the primary HDU that we modified. If you wanted to write out the newly modified primary HDU and have that table go along with it, or any other HDUs that were associated with it, here we ran hdu.write_to, but down here, HDU list has all of the HDUs in the file. So you can do hdu list.write_to, and it will write all of them, along with the modified primary. So that's important too. To create a FITS file from scratch, there are kind of a lot of ways of doing this. The simplest is if you just have like a single array, that would go into a primary HDU. So you can make a primary HDU object from scratch. This shows one way of doing it. You don't have to pass it any arguments, but once it's already created, you can just assign some data to it, like this Numpy array of just some random data, 128 by 128. The header will already be in there by default. It will come with a default sort of valid header. Now, since I already assigned the data, it's put in the correct n-axis keywords and the correct bitpix keyword as well for that particular data array. And I can put some other things into that header, like the telescope. This is a point worth making. When you put header keywords in, it's, for standard keywords anyways, it's case insensitive. So you can write the keyword in lowercase, but it will still actually put it in the header in uppercase as is standard. So this does support, however, some kind of more non-standard conventions for fits keywords, probably most notably the ESO's hierarch convention for putting longer keywords into a fits header. And the neat thing about the hierarch convention is that the head keywords, I think, are also case sensitive, or at the very least they can contain any case. So that also works. But if you don't use that particular convention, you don't have to worry about it. So we've created a primary HDU, assigned it some data, put some keywords in the header, and then just as before, we can just write this out to a new file with hdu.write_to. And before I go into convenience functions, how am I on time? Do I like?
You're taking about 20 minutes now.
Okay, I'll just move through the rest of this then. There were some other things I had in a later version of the notebook that you can look up on the website that shows how you can modify some fits files in place. So here we're kind of modifying a fits file and then writing it out to a new file, but you can also take an existing file, modify it in place, and just save the changes directly out to the existing file rather than creating a copy. And it also goes into how you can create multi-extension fits files. So one last thing to point out here are the convenience functions. These are very useful to use at sort of the command line interactive sessions when you're exploring data. So for example, rather than doing fits.open blah, blah, blah file name, you can just say, I want the data that's in this fits file, and I want the header that's in this fits file, and you can use get data and get header for those. Now by default, that's taking the data and header out of the primary HDU. One kind of thing to note about, I think, get data is that if the primary HDU does not contain any data, which is common, for example, for a lot of HST files, it will actually return the data from the first extension that contains data, which is usually like the first Sci extension. So that's also kind of worth being aware of. But if you want to be specific, which you probably should, you can tell it actually get data and provide this xname argument, which says, give me the data of the actual HDU with the name energies. Or you can just give it by its numeric index. And tables, I'm not going to spend a whole lot of time on tables. Right now, the AstroPy fits module has the old table interface that was with PyFits that was based on Numpy. It's fairly similar to the table interface that Tom just showed you, but not as powerful. But this file contains a table, this point source catalog, and you can actually ask what are the columns in that table with the .columns attribute. And I know for a fact that this table contains a lot of columns, so I'm just going to print out the first 5, for example. And so you've got some coordinates, like some RA and dec, and you can just access those by doing the .data and then give the column name. Or alternately, as Tom showed, rather than going through io.fits, you can also get to fits tables using the AstroPy table object and give the same file name. And it knows how to deal with fits tables pretty well, except for all those warnings, but that has to do with the units. And so it'll print that whole table out for you, or you could just print part of the table. In a future version of AstroPy, this is going to be sort of the default interface for fits tables. So when you open a fits file, you go to a table HDU and access the .data attribute, you'll get back one of these AstroPy tables. The reason that isn't there quite yet is because AstroPy tables don't support all of fully support all of the features that some types of fits tables have, but it works for probably like most of them that you'll find, just not all. Okay, so a few practical exercises. Try and read in one of your own fits files if you have any on your laptop, and plot the array values in matplotlib using imshow, for example. Look at the header, try to extract individual values. I think most of you are probably already used to doing this, but if you're not, go ahead and give it a go, and I'll be around to help. The second is to read in that LAT point source catalog. That was that last table file I opened above, this GLL_PSZ v8 in your data directory. So read that in, make a scatter plot of the galactic coordinates of the sources, complete with axis labels, and bonus points if you can make the plot go between minus 180 degrees and 180 instead of 0 to 360. Note that the point source catalog contains the galactic coordinates, so there's no need to do the conversions. And finally, using matplotlib, make an all-sky plot of the LAT background model in the plot carré projection using the LAT point source catalog overlaid with markers. These are some pretty involved exercises, so don't worry if you don't get through all of them, but they're definitely worth a try. So you should try doing this using just astropy.io.fits, numpy, and matplotlib. There's no WCS conversion necessarily required here. And I'm going to actually go ahead and get started on those in case your matplotlib foo isn't like that, and I know mine isn't. I'm going to go ahead and actually start typing in some kind of framework for doing each of these exercises for at least the plotting parts. And your job will just be to get the data out of the related fits files. So both of these exercises are using the fits files that were opened earlier in this particular tutorial page. Any questions while people get started? So I've got some hints up there for the second level 2 exercise. And you have the solutions also, so if you want to refer to that, that's fine too. Not usually. Should we move on? Yep. Okay. So if you didn't finish all of the exercises, the solutions are in the solution notebook you have. I guess the only thing to go over really quick is to get these galactic latitude and longitude pairs from the point source catalog. You would just do fits.open with the file name. That returns the HDU list. Now the table is in the second HDU. That's important to note. And you would just do table.data glat and table.data glon. And that should give it to you. For the second one, I'll skip that for time, but what you should have gotten is a nice plot showing the image with the source points plotted on top of it. Right.
So I'm going to try to carry on now with the ASCII tables. So ASCII data table just simply refers to a tabular data set where the values are encoded in ASCII in sort of a row-oriented format. And you see this all the time. They're fact-like for scientists. They're convenient, but it can be a pain to read them, especially because there are so many different formats. So the Astropy Io ASCII does provide methods for reading and writing these in a wide range of formats. And while this package isn't the fastest reader-writer, and probably Pandas takes the record for the fastest reader at this time, io.ascii is one of the more flexible ones. And actually, we have a student working this summer for Google Summer of Code that's trying to make it fast. The following does show the list of ASCII formats that are available. You can go to the web page to see the full list, but what we start with is simply the basic, which is sort of customizable delimiters and the header configurations. Then we have a bunch of sort of astronomy-specific ones like CDS, which is where you'll see tables coming from AppJ or Vizier, DO from this IRAF package. You see those floating around. Fixed width is sort of specialized, but sometimes you see tables that have been formatted sort of by a human to look nice to a human, but those are actually sometimes difficult to parse. So you can actually get a lot of information from this fixed width gallery that has a ton of examples. IPAC, you can read and write LaTeX tables. And finally, this S extractor, which is sort of another bizarre format. And the fun part about some of these ASCII tables is that they're either not really documented to any specification, or sometimes the tables don't even match the specification, and specification in one case is basically a Fortran program somewhere that is guaranteed to read them. So makes it a little bit of a challenge, but we try. So in terms of interface, when you're using io.ascii, there's actually two sort of equally valid ways of reading and writing. The first is directly with this Astro Pi Io.ascii module, And then the second is using the unified I/O interface with the table class. And internally, there's actually no difference at all between these two methods. This is unlike, as Eric mentioned, fits or VO table, where there's actually the table unified I/O interface only supports a subset of the functionality. In this case, it's exactly the same. It depends a little bit on style. The one is a functional interface. So this shows an example here of importing from astropy.io, import ASCII, and then you call a function, read data, and you get out your pets, or you write like this. And the key thing here is in terms of how this format is specified. Table interface is a little bit, is basically the same, but it looks a little bit different. And the key thing here to note is that the format here with ASCII, you just have this LaTeX, and down here, let's see, with table, you have to have this ASCII prefix when you're specifying the format. So overall, we do recommend generally using the table interface because eventually this is going to be supported fully for fits and VO tables, and there will be just sort of a single syntax which lets you read all the tables. So let's just jump into reading the tables. So first, you'd have to do your imports. And here's an example table. Okay. And so this is basically the lines is just a single string, which looks like the kind of text file that your collaborator might send to you. And so you just call table.read with that lines in there, tell it it's an ASCII table, and you get out a table that looks like so. It's pretty straightforward. So what I want to do now is just sort of focus on the arguments and go through it. There's a fair number of arguments that you have to master in order to read the large variety of tables that you have. And the first and most important actually is just the table argument. You want to just show me the table. And this is actually one of the more flexible parts of astropy.read, which is saying that you can give this table either as the name of a file as a string, or a single string that contains all of the table lines separated by new lines. And that's what I was doing up here. You can give a file-like object, a Python file-like object with a callable read, or else a list of strings. And so it lets you, it takes a bunch of different, it's quite flexible and handles most of the common use cases. The next is the format. So generally you have to tell it at some level what the format is, although ASCII.read or table.read has quite a bit of guessing functionality built in. So frequently you don't have to specifically tell the format. With table.read, the generic way of just saying it's an ASCII table and try to guess the format is that you say format equals ASCII. Or if you know a little bit more, you can tell it ASCII and then the format name like CDS or IPAC. So that's in table. If you're using ASCII, you don't have to generally say what the format is unless it's a specific one like CDS or IPAC or LaTeX. So here we have an example of what's clearly a LaTeX table. And I'm going to read that by telling it that the format is ASCII.LaTeX. But note that I think even if I hadn't told it that it's LaTeX, it still would have worked. So it automatically can guess a lot of formats. So that brings us to the next argument, the guess. And this is an important point about effectively using the ASCII reader, which is that the default behavior is it tries to actually guess the table format, which frequently works. So here's an example of something with a commented header, which will probably choke a lot of readers like Pandas or NumPy Gen for text. because the column names are in this commented header. But in fact, it works in io.ascii or table.read for ASCII. And the basic idea here is this sort of will it blend. The table reader tries that table with a whole bunch of formats. You throw the input data in and see if something nice comes out. And most of the time, if the table reader, the different types of formats will sort of give out garbage or throw an exception. So the first time the table reader comes back with something nice that looks like a reasonable table, guessing stops and the table gets returned. So in this case, the order of the input formats is fairly carefully tuned in order to sort of maximize the likelihood of guessing the right format. And also this whole idea of what's a nice looking table is based on some assumptions that might not always be the case. So here's an example where guessing doesn't work. So what you'll see in this case, and this is because this delimiter is not one of the supported default delimiters. You see when you read a table like this and it doesn't work, you'll get this big long trace back, and basically what that's doing is it's telling you all of the different options that it tried. So in this case, it started with reading a basic value, and then it went down through tab delimited, CDS format, DO format, S-extractor, IPEC, LaTeX. All of those, it tried to read the table that way and it failed. And in fact, in this case, it tried cycling through a whole bunch of different delimiters, and none of that worked. This strict names here that you see equals true. What that's saying is that it's not going to accept a table where the column names are something weird like a pipe sign or an ampersand. It should be something that probably starts with a letter and is reasonable in that way. So when that happens, you have to eventually give ASCII.read a little bit of help. And so in this case, what we would be doing is first diagnosing the problem. And to do that, usually what you want to do is set guess equals to false. And the reason for that is when guess equals true, all it knows is that all of these individual readers failed. But it doesn't tell you why. That would just be too verbose. So in this case, we tell it that, well, we know the table is just kind of a basic table. It's not any one of the really domain-specific or package-specific formats like LaTeX. So I read it, and it says the number of header columns, 3, is inconsistent with data columns, and then it says what it guessed for the header columns and then what it guessed for the first set of data columns. So you can immediately look at this and say, that ampersand really shouldn't be the name of a header column, and what it tried to do here was use space delimiting, and it failed. So let's just give it a little bit of information, and namely, what's the delimiter? And you do this, and it works. So this is part of the art of effectively reading tables, and you'll get tables from your collaborator that are just in all kinds of screwy formats. People don't usually think about making their tables machine readable when they're taking notes, and so the goal is to always be able to read any table that someone gives to you. The next thing we have to worry about are the delimiter, which we just introduced, the comment, and the quote char, and these basically define the table characteristics. Delimiter is pretty obvious. The comment is a regular expression that defines which kind of lines are supposed to be ignored in the parsing. And finally, the quote char, which is what character is used for quoting. So if you have a space-delimited file, but you want to have a field that has spaces inside, you need to quote it. So here is an example of a horrible table, which uses the star for the delimiter, ampersand, and then quotes with a little caret. And please don't use that, but it works.
I have a question.
Yeah.
Why did the ampersand work up in the LaTeX table?
Up in LaTeX. That's because the LaTeX reader knows about ampersand, and in LaTeX files, the ampersand is the column delimiter. So that's where you get a, sort of a specific reader that it not only knows about the ampersand here, but it was able to, well, let's see, I mean, it knows that these, the double slashes are the end of a row.
So what clued it in what part of that clued it in that it was LaTeX?
Oh, yeah, that's a good question. That's where the guessing comes in, which is basically it tried everything else and nothing else worked, but finally it got to the LaTeX and it said, okay, does this work as a LaTeX table? And everything fit. The LaTeX table has a very specific structure and format, so if it gets all the way through to the end of parsing this and nothing choked, then it says, I've got it.
But just to add, I mean, the reason that the LaTeX reader didn't work for the other example is because it doesn't have the double backslashes or things like that. So
Yes, exactly. Yeah, I mean, this doesn't. Yeah, I mean, the LaTeX actually has to start with a table, and then tabular, and it needs to meet the whole requirements for being a table. Okay, where are we? Quote chart. So this is a sort of a tricky part of the reading process, which is basically sometimes the tables don't start with a header line and then have data right after that and have data going all the way to the end. ASCII.read ignores completely blank lines, but sometimes people, they'll give you a table where they've just written stuff at the top, or there's a header line and then just random text, whatnot. I mean, you get this kind of thing all the time, and the goal of ASCII.read is to be able to read any table without actually getting in and modifying the actual text of the table. So header start tells you the line where the header begins, and the important thing here is that comment lines aren't in that count, and counting starts from 0. So basically when ASCII.read is parsing it, the first thing it does essentially is throw out the comment lines. Likewise, data start specifies the index where the data begins, and again, that begins counting from 0 and doesn't include comment lines, and data end is sort of the same, but it means what line does the data end. And most of the time, you actually want to specify from the end of the file. So say someone or some program creates a table with 3 lines of useless non-table data at the end, and you get that all the time. You would specify -3, which means ignore the last 3 lines of the table, no matter how long it is. So here's an example which has some irrelevant stuff, and then a commented outline, then the actual headers, a blank line, then some more junk, then a couple of data lines, and then more lines of stuff at the end. And so I've annotated at the right side, what ASCII.read is going to do with this. So in this case, you need to have header start here, data start here at 3, and then the data end there. So I've done that. I've done a read command with the header start equals 1, the data start equals 3, and the data end is -2, and I told it not to guess. And voila, it works. So one of the things is that frequently ASCII tables don't have any type information regarding the columns in the table itself, and so that has to be inferred automatically. Most of the time it works correctly. Basically, you try the value as a float, you try it as an int, you try it as a string, and one of those is going to work. So sometimes, however, it can get fooled. Like if I have a table like so, where you have 1, 2, 3, 4, 1, 2, 3, 4, and this was actually meant to be a character. When you go and read that, it does automatic type inference, and it actually declared that both of these columns were integers. This I8 tells us that it went through, it parsed this, and it saw that it was a 1, and 1 looks Well, it can be it can be converted into an integer, and it did that. So there's some mechanism which is, it's a little bit, it's meant to be very general. I think that we probably want to improve this to make it a little bit easier to use. But basically, if you want to specify a particular type for a column, you just have to make this dictionary that is keyed by the column name, which in this case is called char or float, corresponding to these column headers here, and give it a list of values. And the point here is that you can actually specify a list of things to try, and it'll try those in order. And so this just means make this be a string and make this be a float. And voila, we read the table, and indeed we see that this one has been converted into a one-character long string, and the other one has been converted into a float.
Will that converter figure out the correct string length? Because I've had trouble
Yeah.
perhaps where you read and the first line has 3 characters in the name, but the nth line has 8.
Yeah, no, it always uses all of the data. ASCII.read never ever assumes that the first 10 rows or the first 100 rows represent all of the data. So there's a performance penalty in that, because it does have to, it reads in everything, the entire table, into a data structure, and then tries to convert the whole thing at once. Okay, so the last thing is, I think this is, well, we're getting to the end of the parameters or the arguments. We have names, include names, and exclude names. So sometimes you'll get a table and it's got 100 columns and you actually only want 3 of them. So you can, sorry, that's the second part of the example. The first, actually more common example is that you get a table with no header information. Someone just gives you the numbers, and you actually want to read that in and assign meaningful names. And I've assigned A, B, and C, which isn't that meaningful, but you see that when we read this data, notice that we didn't have to tell it that there weren't any headers, because it was running in this strict mode where it first tried to read this and it said that the header is 1, 2, and 3, and the column data are 4, 5, and 6. And so when you have this strict names equals true, which is another argument, it won't allow column names 1, 2, and 3, and so that would fail. So it failed through to another or basically the no header reader, which just says that these are the data and assign default names. Note that if I just did table.read lines, sorry, can't type. It'll automatically assign column names, which works, but it's not as nice. So this is the second example where someone has given you a table with a lot of columns, and you only want a few of them. So you can just say include names equals, and it's going to discard all of these and return you a table with only the include names. You can flip that around and exclude a couple of names if there's just a couple of table columns you don't want. And finally, the fill values, fill include names, and fill exclude names. This all has to do with handling tables that where they've marked missing data with a particular value. Sometimes you'll get a table where they have a -999, which means a missing value. And so this is the mechanism that you'll use for actually marking those particular values as masked in the output table. And I don't really have time to get into that today. It's a little, the syntax, and it's a powerful method, but the syntax is a little bit intricate, and you can just read through that in the documentation. Finally, writing tables. Writing tables is relatively boring or easy task compared to reading them somehow, because you know exactly what you want. So the parameters for write are fairly simple. So what I'm going to do is just give you a few examples instead of going through those exhaustively. So here is a simple case where I'm going to read in a table into the t-value and give it some units. So I'm assigning the unit for the y column to be meters per second and reading that in. And now I'm just going to do the simplest write. Okay, so in this case, I've written to sys.standardout. So the first argument is always the output file, which could be the name of a file or it could be a file object, Python file object, and I told it to do ASCII. And that's pretty straightforward. Notice that it's the default is space delimited and it's inserted quotes around the values that actually have spaces in them. The next thing would be comma delimited. Pretty straightforward. We can get a little bit fancier, and in this case I'm demonstrating the functional interface by calling ascii.write, and in that case you need to supply the table as the first argument. So you see either start from the table.write or ascii.write and the table. It's fairly similar, but we don't need to put this ASCII in front. And we get a AAS deluxe table, which you can then insert into your paper and you're good to go. Getting a little bit fancier. So we're writing this into the IPAC format, and one of the things I did here was specify the formats. And so if you want to have some sort of fixed formatting, notice that the raw data value here is 4.01234, and in this case I wanted just 4 digits of precision, and so that came out here as 4.0123 because I specified this formats. You can change the names of the output columns. So this list of names has to be exactly the same length as the number of columns. And finally, you can specify fill values. So in the original table, let's say that we had a value of -99, which we wanted to indicate missing data. But in the published values or published table, you want to have a ... So you would say fill values, change -99 to a ... and you get your LaTeX table. So any questions? Alrighty. So let's jump to the exercises. So basically what we're going to do is just try to read some tables. And the important part here is that there should be data files in the data/ASCII subdirectory. You want to read each of these tables and show the contents. And so the basic pattern that you want to use is highlighted here, where you're going to do table.read and then the file name, which will be data/ASCII/ and then each of the file names that I listed here. And you need to specify a format and any other arguments to get that to read. Well, you can just go on and look at level 2. Level 2 exercise has to do with examining the metadata, which is where the Astropy tables can contain a little bit more information about the data table. So.
going to start the last section, which is about coordinates. So we're actually not going to skip over showing the solutions for the io.ascii section, but all the solutions are available through the main page for the tutorials. Okay, and if you have any questions about them, then you can ask Tom or any of us after this. So the last section is about celestial coordinates, and this is something that has changed in the most recent unreleased version of Astro Pi. So that's why we got you to install the release candidate before. The idea, so we've actually gone through several iterations with the API, and this is something that we've converged to now that is going to stay the way it is. So rather than teach you the old way, we're going to teach you the new way of dealing with coordinates. Okay, the fundamental object now in the AstroPy coordinates package that you'll be using is called SciCoord. So SciCoord is you can import it, of course, from astropy.coordinates, import SciCoord. And the idea is that it's a very high-level class which allows you to, essentially, you can create coordinate objects in many different ways, and it's very flexible. You can also, if you want, use kind of more lower-level classes which are more rigorous, but this is usually the nice kind of user interface. Okay. So there's many ways you can create coordinates. So this is just one of them. You can create, for example, you can say that you want to create a SciCoord object with, for example, an array which is equal to, this quantity. Okay, so we talked about AstroPy quantities, and so you have array equals 10.6, etc. times degrees, and then you pass a declination also in degrees. And you can specify a coordinate frame. Okay, so the frame can be something like ICRS or FK5, FK4, galactic for galactic coordinates, and we're going to add more frames over time. Okay, so if I do this, it creates this SciCoord object. Now, I should also mention, this is very important, that if you don't specify a frame, then the frame defaults to ICRS. Okay, so that's very important. Now, of course, you can pass these quantities. You can also pass, for example, strings, and it knows how to pass a certain subset of strings. So, for example, this format, which is reasonably common, so you have the values separated by these letters to indicate hours, minutes, seconds. You can basically pass that and tell it to interpret it as an ICRS coordinate. And then that will actually go and transform the string values into floating point values, quantities internally. And there's other things you can do. You can also pass, I think, just plain values without the units and then pass the units as a separate argument, or there's different things like this. But the point is, there's different ways you can instantiate this. You can also, I will show this in a minute in more detail, you can also pass arrays. So coordinates don't have to be just a single value, but they can be a set of values. Okay. Once you have a coordinate object, then you can access the values inside by using attributes which depend on the type of the coordinate. So for an ICRS coordinate or FK5 or FK4, you can access the array angle by doing c.array, and you'll see that it actually renders it in LaTeX in the notebook. And so it's basically returning a string. It's returning an angle object which is represented by a string here. But you can then also say that, for example, you want to get the value in hours. Okay, so then it will actually. This is a shortcut. You could say array is basically a quantity. So you can do something like 2 and then say hour angle. Okay, this will work. But you can also if you do this and then you do value, you would actually get the value. But rather than having to type all this, we have this shortcut where you can do c.array.hour, and that gives you the value in hours. Okay, if you do array.hms, it's also another convenience. It returns a tuple of the 3 values for the hour, minute, seconds. Okay. Declination is the same, so declination is again a quantity that's being formatted here nicely as an angle. And then you can also say, for example, you want to access the value in radians. Okay. All right, so that's how you create and access the data in coordinate objects. There's so most of the time, just if you want to represent coordinates, it's usually because you want to convert them to something else. So there's different ways that you can convert, and I'm going to start with the easiest way, which is essentially the least flexible way, but it covers most common use cases. If you have a coordinate object and then you do basically c.galactic, okay, it doesn't matter what coordinate system C is in, it will try to convert it to galactic coordinates. Okay, so using the object from before, I will do c.galactic, and you can see this sky chord now has galactic in brackets here, which indicates the frame that you're in. And then, for example, I could do c.fk5, and it will convert it from ICRS to fk5. Now the problem is, this basically is, so first, this is equivalent to doing something. You can use this transform2 method, and you can pass strings to this transform2 method. Okay, so you can pass a string that says galactic. Now the reason why we have, and you get the same as before, but the reason we have this is just because it's shorter to type. Okay, and there's many kind of common use cases like this where it's useful to have just a fast way of doing it. The reason we have the transform2 method is actually, and we don't just have these things up here, is because you basically, if it was just that we were passing strings to it, then it wouldn't matter and we could just have these attributes. But the thing is that, for example, an FK5 frame can have a different equinox, okay? And there's no way to give this kind of information when you're passing a string. And so we have this system where you can create frame objects in Astro Pi coordinates, and you can actually set various parameters for the frame. So ICRS doesn't really have any parameters, but FK5, for example, has an equinox. It can have an observing time or date, and same goes for FK4, for example. And you can imagine, for example, the altitude azimuth system would then also require some location on the Earth, some date at which you're observing things. So you need to have all this information. And so basically, this is just an example. If you do from astropy.coordinates import fk5, then you can basically instantiate an fk5 frame with a parameter that's not just the default. Okay, if before you were doing c.fk5 here, this will use the default values. Okay, so for fk5, the default equinox is J2000. Here you can basically set the equinox to what you want. Okay. And in fact, you can. This actually just brings me to mention very briefly something that I'm not going to go into in detail here. But SciCoord covers celestial coordinates, but there's also the ability in AstroPy to represent time coordinates. Okay, and so that's in the astropy.time subpackage. And I'll just let's see. I insert a cell here. You can basically. Let's see, import time. So you can import the time class, and then basically here, when you pass this kind of equinox, you could actually pass any kind of valid time object. Okay, so it doesn't just have to be J2010. So that shows a bit the integration between the packages. So all you need to know is that time is the kind of equivalent of SciCoord, but for time instead of celestial coordinates. Okay, and I'm not going to say anything more about it. So let's see, I'll just delete this to avoid confusion. So once you've created your frame, then you can pass it to transform2. Okay, and you'll see that here it says, it's a SciCoord fk5 with equinox, this, and then basically RA and dec, these values. Okay, so this is how you can basically then have any kind of arbitrary frames. You can even, if you're working in an application where there's not a coordinate frame that already exists, you can even create your own frames and link them in to the what we call the transformation graph, which says how to go from certain frames to other frames. Okay, so since we're running short on time, I'm just going to show a fun feature here, which basically is that if you, for those of you who know the Simbad database, you can basically give a name and get coordinates back. So we have an interface to that. You can instantiate coordinates with SciCoord.fromName, and then you can give it the name of an object, and it will go, and if the internet works, it will return a SciCoord object. Okay, so this is just got to, most of the time you shouldn't rely on the Simbad coordinates as being, ultra precise. For example, M16 is actually an object that's, I guess several arc minutes across. But it can be useful for very kind of quick calculations. Okay. The last topic that I'll talk about is how to use arrays in coordinates. So I mentioned that sometimes if you have 1 million coordinates, for example, you do not want to have to create 1 million SciCoord objects. Okay, it's just the memory will just explode on the computer, because it's not just about the memory of the values that you're storing in it. Each instance of a class takes, you know, some memory, and it just it basically goes out of control if you try to instantiate 1 million of them. So what you would want to do is you want to pass just arrays instead of values, okay, and then it should work. So I'll just show an actual example with a data file here. I'm going to import, so to show a little bit the integration with the table class, so I'm going to use the table class to read an IPAC table, okay, which is from the 2MAS point source catalog. So I can look at the table here. It has a number of columns, and okay, many columns. And two of the interesting columns are so it has a column called array and dec, okay, the two first columns, and those are basically as floating point values in degrees, okay. So what I can do is I can then just say I want to create essentially a SciCoord object using the array and dec column. Now, since the columns in an AstroPy table are not full quantities, at the moment you have to explicitly give the unit still here. But this will work much better in the future. So here you do TRA, which is just a Numpy array, times u.deg, and then tdec times u.deg, and then you can specify the frame that it's in. Okay, and once you do this, if I look, for example, at c.ra, which gives me the array quantities, and then .degree, which gives me the value in degrees, then I'll get a Numpy array back, okay, which contains all the values in degrees. So those are the same values that I put in. Okay. But so here's another fun thing you can do is that since there's also a column which is the array and dec in string format, then we can also try to instantiate the coordinate object from these. Now, of course, if you have the floating point values, you should just use those, but this is just for demonstration. Sometimes you don't have the floating point values. Okay, so for example, here you can do SciCoord, and then you can give the two columns, which are the strings, clon and clat, and then the frame. And if you do this, it takes a little bit longer, but then it runs, and again, if I do c.ra.degree, then it returns the values in degrees. Okay. All right. So before, just one last word is that this is a new kind of functionality in 0.4, and so if you run it across any bugs or anything to do with that, for example, even now or this week, then please let us know, and maybe we can even fix it for the final 0.4 release. So there's a few exercises below, which are just a few small exercises, but I think we'll leave just 5 or 6 minutes, and then we'll just have a couple of closing remarks. Okay, so let us know if you have any questions about these.
so that I could pick a point and choose spherical coordinates from some Cartesian point.
Let's see.
The very easiest way is actually,
Yeah.
I mean, you can use SciPy, and you just give it, you know, an X, Y, and Z, and then you say representation equals Cartesian,
Okay. What would fancy for that? Would just
ICRS. I mean, you know, at least at the highest level, it's very simple to do that and think about it. You can use the representations directly. They're not as quite as user friendly,
Yeah.
but they do have. I mean,
Oh, tell that.
it all that's really why the representations are there, is just to handle sort of abstract data that isn't supposed to be in any
Is
particular
it a
framework.
dash here?
Okay. Cool. Thanks.
Oh, there it is.
That's what I want. Just take a little while to get there. Yeah, I was happy when we finally did this. Started writing, I was like, okay, I'm writing things the way I somehow though, it was actually, something I didn't quite expect was that we were just gonna focus on SciPy core as the interface for users. I mean, the first thing when I was writing this, I was like, well, it's a handy thing, there will be ICRS featured as, you know, yeah, actually, I was just looking at your copy and the fact that we default to ICRS now. I mean, it just took away this whole discussion about help writing, which is complicated and confusing. And,
So I'm looking through the computer, and when I go to do this line, I get these errors. And but if I take off the times degree unit, it works. So did it know already that it was in degrees?
Yes, that would be version 1. So managing.
Oh, which version? Just today I got that.
The RC one.
That wasn't in any.
it's interesting.
Oh. Oh, okay.
Oh, what's going on there?
Yeah, you're right. I think now, yes. So just a quick note on the notes. When you pass, now it turns out that we actually made it that you can actually pass columns. So the column actually did have the unit of degrees in it, and even though when you access the column, it's not a proper quantity, the coordinate object knows how to recognize that the column has units, and then just uses that. So you don't actually need to specify. If you use the table column and the units are given in the table, you don't need to then multiply by the unit. Okay.
But when you multiply TRA times U dot degree, you got an array of quantities?
Does that work? I don't think it does.
Well, do that again, that looks wrong.
I think there's just some duck typing in the. Oh, sorry. Yep, that doesn't work. But
No, we do TRA times U dot degree.
it's weird.
What, I mean,
Yeah, I know this looks wrong. Yeah.
that doesn't look right.
Oh, this is the.
Mass array for list of oh, yeah.
But if if you do, I think the key is this. Oops. Yep, it's in degrees. So we have some duck typing now that it recognizes the unit on the column. So it's good.
Well, I guess this is part of the quantity integration, but
Right.
applying a table column times a unit should give you,
Yeah.
you know,
There's a bug.
basically
Yeah.
it must have turned into an object array.
But you should, yeah. It's a bug. You should.
You found the bug in 5 minutes.
Yep.
Wednesday afternoon is set the whole afternoon, but the Astropy is right after the first.
Okay, so since it's 12, I think we'll just wrap up. I mean, you're welcome to just, I think, stay here. We're not going to get kicked out anytime soon, I guess, until there's a tutorial probably starting at 1, but you can probably stay another 10, 15 minutes if you want. Just to wrap up, I'll say that on Wednesday afternoon from 1:30 to 4:30, there's going to be the astronomy mini symposium, which will be in room 203. So there'll be 6 talks on kind of astronomy-related Python projects, and in particular at 3:30 on Wednesday, Perry will be giving an overview of a talk about Astro Pi, and in particular where things that we're planning in future. And so if you're interested in hearing about that, then please come along to the talk. But otherwise, I think also on the sprints later in the week, we're going to plan AstroPi related sprint. So if you're interested in learning how to contribute to AstroPi, then please come along, and we'll be very happy to help you get set up with contributing. And we'll give more information about that at the actual mini symposium. Okay, cool. So I think we can stop there. Thanks.